Hello and welcome to another episode of Math with Sohn. Today we're going to be doing another one from June 2024, and this is paper 2-3. All right, and we are doing the last problem, which is the modern physics question, which involves a nuclei of some atom I've never heard, samarium, and it has apparently 62 protons and 85 neutrons. Which makes it an isotope because we don't have an equal amount of each of those, which also makes it unstable, which is probably why it's going to decay at some point. Okay, and it wants to know what is going to be the A, the Z of this. So I would write this as SM, and then I would put in the total, I call it the nuclide number here, and then this is where the protons go on the bottom. So we have in total 62 protons, so this is going to be 62 with the SM, and that would represent the X is the SM, the 62 is the Z, and then the A is going to need to be the total, so you would just have to add up the 62 and the 85, and 62 plus 85 is apparently 147, so the A value is 147, the 62 is Z, and the SM is the X. Okay, that was only a one-pointer, so we don't have to go too far into that. All right, let's make sure I did my math right. I did. And AICE also liked the SM as well. So you would need to write all three of those. And you could put them on the top or a little bit to the left. It's up to you. Now here's a unique one. I don't see it very often, but it is still tested occasionally. And that is the difference between gamma radiation and alpha radiation. Now remember, gamma radiation is going to be pure energy. Okay, that is a photon of radiation. And because it is a photon, it can be in any specific amount, as well as beta. Okay, it could also be beta. So beta particles could also be in any specific amount of kinetic energy released when it undergoes that decay. Now, do remember that the energy of any of these is going to be caused by the mass defect. Okay, so whenever we decay from this samarium into something else, whether that be alpha, beta, or anything else, it releases energy because some of the mass is gone. Like it poofs out of existence and turns into energy. And that all comes from the E is equal to mc squared equation, famously known by Einstein. So the amount of mass that is lost in the decay process, even though it has to maintain the same amount of charge, so it maintains the same amount of charge, but some of the mass is released and turned into energy. Okay, normally that energy is gamma radiation, but it could also turn some of that energy and put it into the alpha particles or the beta particles, depending on what it is actually releasing in the decay process. All right, all that being said, here we have a vertical line. And because we have a vertical line, that tells us that the kinetic energy is gotta be whatever it is. It is whatever joules of energy is here, which is not a lot, will be whatever it is, regardless of how many particles are decayed within the spectrum. They always have the same amount of kinetic energy. And with that being said, we are having to explain from this figure why do we know that it is alpha particles and not beta particles. Okay, so alpha particles, remember alpha particles are 2 and 4. They are the nuclei of a helium atom, and they are the biggest of the radioactive decays. And when alpha decay occurs, it is the only particle that is decayed. Only particle that is decayed. It could also release some energy. So remember, gamma is not a particle. Gamma is light. It is pure energy. But alpha particles, when they decay, it is only an alpha particle. All right. When beta particles decay, they will decay whether it is beta positive or beta negative. It will have a neutrino with it. And because it has a neutrino with it, that means that the beta particle might have more kinetic energy in some scenarios than in other scenarios, because we don't know how much of that kinetic energy is going to be imparted onto each of them. Okay? So, because of that, this cannot be a beta particle and has to be an alpha particle. That's the easiest way that I've come across it. But if you just memorize it, that the kinetic energy of alpha is always discrete, where the kinetic energy of beta particles, whether that be beta particle positive or beta particle negative, it can or is continuous. Okay? And that is all you have to really know. Now, I do want to point out that even though the kinetic energy is discrete and the kinetic energy of the beta particles is continuous, that does not mean that the momentum of each of those would be different. Okay, so the momentum would end up being the same. You can think of it as like a bomb going off. Not an atomic bomb, but like if we have this atom and it decides to split up into an alpha particle and some other particle, like this is going to decay, apparently, if we keep reading, into neodymium, whatever that is. So if we have an alpha and a neodymium, the momentum of each of these will be the same. The neodymium, I'm assuming, is going to be much, much bigger than this alpha particle, so its kinetic energy will be much less, will be moving much smaller, good gosh, will be going much slower than the alpha particle, but the momentums, at least the magnitudes, should be the same, because if the original momentum was 0, if this original atom wasn't moving, when they split up, they will have to be having the same net momentum as the original, which means the momentum here and the momentum here would have to cancel out. That's a lot of talking. I'm sorry, I got distracted. All right. So here, the isotope of this atom decays into this atom. I don't want to butcher the words, but samarium decays into this. Remember, we are told it was an alpha decay. So that means that we had the samarium, which had 147 and 62. It turned into a Nd plus an alpha particle, and also probably plus some sort of energy in the form of gamma, which kind of looks like a Y. You don't necessarily have to write the gamma, but it's smart. I do, just because I like it. All right, and then it wants to know, give the radioactive decay equation. So we're doing it. Include the nucleon number and the proton number of all particles involved. So let's start with the alpha, which is a 4, 2. 4 is the nucleon number, and 2 is the proton number. Well, if we took 2 protons away, that means that we have 60 for this new atom. And if we took 4 of the nucleons away, we have 143 for that. And that's it. Ta-da! That's all she wrote. Okay? Yeah. Moving on. We got a little bit more with this one. Let's see. I haven't read this one in advance, so let's see. A baryon is composed of 3 quarks, all with different flavors. Okay, so baryon is composed of 3 quarks, all with different flavors or different colors. The baryon has a charge of 0. So in order to have a charge of 0, it must be some combination of tops and bottoms. So 2 of the quarks are an up quark and a bottom quark. All right. So the up quark will have a charge of positive 2/3. The bottom quark will have a charge of negative 1/3 of the elementary charge. The third quark will have to be a negative 1/3 as well. So that third quark, that third unknown quark, is also going to have to be negative 1/3, because negative 1/3 and negative 1/3 and 2/3 makes 0. So what is that charge in the terms of the elementary charge? Well, it would be negative 1/3 E. And if you wanted to figure out that in coulombs, which occasionally you have to, you'd have to do negative 1/3 of the elementary charge, which is 1.9 times 10 to the negative 31st. It might be negative 19th. But that is on your formula sheet. You don't have to have that memorized. I think it's negative 31st, though. Don't need it, though. We just got the negative 1/3. And then it says, state the possible flavor of that third quark in the baryon. And a baryon is a proton or a neutron, just so everybody is aware. And, well, the flavor has to be a negative quark. And it should be one of the regular ones. I would say it is a down, oh my gosh, down, or a strange. You could not allowed to do, you could not do an anti-top or an anti-bottom or an anti-up or any of those, because these regularly have positive 2/3, and if you make it negative by doing anti, negative 2/3 is not what we want. We want just negative 1/3. So it would either be a down or a strange, and you would only have to write one of them. But that's going to do it for this one. Until next time, my friends, stay positive. I will see everybody later. Bye.